right, chapter 8, part 3, dot products and vector projections. Sorry if that's a little small. Dot products and vector projections. Arnie goals. Remember when we found magnitudes? We're going to use some similar formulas to find the dot products, and we're going to use the dot product to find the angle between vectors and the projection of one vector onto another. So some definitions. What the heck is a dot product? This is an operation between two vectors. And it's indicated with this fat dot. And it's kind of like multiplication, but not exactly. Orthogonal vectors are perpendicular to each other. In other words, they would meet at a 90-degree angle. A vector projection is best explained with a diagram. If I've got a vector V and a vector U, the projection of V onto U is how far V travels along the path of U, if you will, and it's written like this: projection of V onto U and work. So this is a unit of physical output. It's usually measured in joules, or not J-U-U-L. That's the unit of destroying your lungs. It's J-O-U-L-E. We often describe work in joules. Yo, down, somebody wrote fake life on the detector in the bathroom. I thought that was ironic. But you know, like, English teachers often debate true irony. I don't know if you're qualified. All right, so dot products of vectors in a plane. So let's imagine I have two vectors. Let's say I've got U with some X component and Y component. I've got V with some other X component and some other Y component. The dot product of U and V is going to be the product of their X components plus the product of their Y components. Now, every year, about 25% of the people miss this because they tell me this is a vector. The dot product is not a vector. It is a scalar. So make a mental note that that's not a vector. It's a scalar. It's just a number, like 27 or 43 or negative 17. It's not a vector. So the result of the dot product is always a scalar. And that is a frequently missed problem. And I'm talking like mega frequently, like 40% of people write a dang vector on there. Now, they usually do okay on the Chapter 8 quiz because they've just had it. But when we get to the Chapter 10, 8, 9, 10 test, a lot of times people will forget, and they'll give me this, you can imagine, in the form of a vector, which is totally wrong. Don't do that. Orthogonal, if and only if A dot B is 0. So two vectors are orthogonal. In other words, perpendicular to each other. And I'm going to use a mathematical term that you may never have seen before. It's if with two F's. It means if and only if the dot product of those two vectors is 0. So two vectors are orthogonal if and only if their dot product is 0. And what that if and only if means is the logic works both ways. So two vectors are orthogonal if A dot B is 0, and if A dot B is 0, the vectors are orthogonal. So the logic works in both directions. That's what that indicates. I think it means the contrapositive is true, if memory serves. It's been a hot minute since I had that class. But math logic, senior year, that was tough. So let's use it. We're going to find the dot product and then determine if the two vectors are orthogonal. So u dot v, not going to be a scalar, or not going to be a vector, it's going to be a scalar. So x1, that's -3 times x2, which is 3, plus y1, which is 4, times y2, which is 6. Okay, so Grayson, are these vectors orthogonal? Correct, they are not. Because they have to be 0. It's not 0, so they are not orthogonal. They would not meet at a right angle, in other words. Questions about this? All right. So let's do one more. They're pretty quick. So u dot v, 2 times -14 plus 7 times 4. Orthogonal or not, Anna? Indeed. Because the dot product is 0, so these two vectors would meet at a right angle. Okay, so here's one for you guys. Find the dot product and tell me orthogonal or not. I know you can do it mentally, just go through the motions. Okay, Ethan, what is the dot product? Does that indicate orthogonality? Somewhat trivial, but you'll make sure to get these gimmies right on the test after having practiced them. Okay, so some properties of the dot product. We're not particularly concerned about these. It's page 501 if memory serves. This one is one you should make note of. We're going to use that pretty frequently. Any vector dotted with itself is the magnitude squared. Speaking of squared magnitudes, here you have some squared magnitudes.
Hey, I like it.
I didn't see it. Okay. You off the north
I
side.
could have just said yes, but
You off the north side.
I said
See, brother.
keeps them up.
375 seconds left there. So if you guys feel a slight vibration in the earth, fear not. It's that Mr. Campbell and myself work the legs. Magnitude squared. Vector dotted with itself is equal to its magnitude squared. This is just a handy little shortcut for finding that value. So we'll use that. So the others are kind of self-explanatory. They're behaviors of the dot product. It is commutative, distributive. You can scale it, and then 0 vector dot product, if you multiply it by 0, you get 0. So let's use the dot product to find this magnitude. So we're going to dot this vector with itself. that's going to be, and actually, I won't bother with that step. So -6 times -6 plus 5 times 5. So that's 36 plus 25 or 61. So that is the magnitude of A squared. So we take the square root and find just the magnitude of A. Radical 61, which does not reduce. 61 is a prime. So its only divisors are 1 in itself. How would you just know that? Well, I know it because I've worked a million math problems. Once you work a million math problems, you'll just know. After that, you could consult a list on the internet. Or just think, like, is it divisible by 2? Is it divisible by 5? Is it divisible by 7? And go work through all the primes that way until you get to halfway. No up to that point, there will be no thereafter. Okay, so here's one for you. Use the dot product to find this magnitude formula using the same procedure you just saw me with. Let me know if you get mixed up. Yes, sir. It's always possible. As is the case with every displacement, it's only considered possible. So distances in general are exclusively possible. So tell me what this is, Peyton.
17.
Not just 17, but there you go. So you were telling me the magnitude squared, so the magnitude itself is the square root of that value. But good job, you had the value right. So here's an important formula. The angle between two vectors. So if we have two vectors under consideration, and we assume that they are in standard position, we can find the angle between them using this formula. Computer, enlarge. Thank you, computer. Isaac Asimov was a science fiction author, most popular in the 1950s, which is sort of the golden age of science fiction, if you will. But he came up with what's called the Laws of Robotics. The first law is robot may never be allowed to harm a human. The second law is robots have to do what humans say, except for conflicts before one, and so forth and so on. So interestingly enough, those things are being taken into consideration now when Elon Musk writes his super AI that's eventually going to run the planet. But he also said you should be nice to technology. You never know how powerful it may become. So say thank you to your computer in the name of Isaac Asimov. So let's use this formula, shall we? Better sound. Way too loud. Okay, so we want to find the angle between U, which is -3, -5, and V, which is 2, -3. So what I need is, first of all, U dot V for that numerator. So that's -3 times 2 plus -5 times -3. So that's -6 plus 15, 9. Now for the denominator, I'll need the magnitudes of both U and V. Found the dot product we needed. Now let's find the magnitude. So I could use the formula I gave you in A2, or we could use what we found today, which is the dot product of the vector dotted with itself under a square root. So -3 squared is 9, -5 squared is 25. So square root of 34 is U's magnitude. Magnitude of V, radical 13. So theta is going to equal the cosine inverse of that ratio. I won't bother to rationalize anything because it's not a final answer. Cosine inverse of 9 divided by, put your denominator in parentheses. Several errors in first period because they didn't put their denominators in parentheses. 64.7 degrees. To the nearest tenth, which was our directive here. Questions about that one? Sure. So those are the magnitudes of the vectors in question. So what I used was the formula that I just showed you, which was and so I said and carried on from there. So that's where these values came from. 34 is U dot U. So the square root of 34 is the magnitude of U. And then 13 is V dot V. And so the square root of 13 is the magnitude of V. Good question. Other questions? Same deal. Remember that the cosine inverse is constrained to be between 0 and 180. So it's constrained to be between 0 and 180, which will always be where we find the smallest angle between two vectors. So if I'm talking about two vectors that share an initial point, there's no way I can write these such that the smallest angle won't be less than or equal to 180. So don't worry about the cosine giving you something false. In this case, it will always be the final answer. Okay, so we want to find the angle theta between these two vectors. Let's find U dot V first. So that's 1 times 2 plus -4 times 6, -24. So that's -22. Find the magnitude of U. So that's going to be the square root of the component squared. So that's 1 squared plus 4 squared. And then the magnitude of V, square root of the component squared. 2 squared is 4. 6 squared is 36. Radical 40. Caleb, what's my perfect square factor here?
4.
Good. So I'll rewrite this as radical 4 times radical 10, or 2 on the square root of 10. So now that we've got all that data, we can plug that into our formula. So that is the cosine theta equals -22 over Radical 17 times 2 on the square root of 10. So theta is going to equal the cosine inverse of that value. Another thing, when you use cosine inverse, make sure you're in degree mode, ladies and gentlemen. If you're in radian mode, you're going to get some weird funky decimal. It'd be like 1.4 or something like that. It won't make a whole lot of sense. So make sure you're in degree mode. Cosine inverse, negative 22 divided by, and notice I'm putting the denominator in parentheses, $147.5 degrees. If I had been in radian mode, I would have gotten this answer. So be careful to check for plausibility. Because if I look at, it's 2.5, if I look at the way these vectors are laid out, you know, positive 1, negative 4 would be something like that, and positive 2, positive 6 would be something like that. So does it make sense that this is 2 degrees? No. So you may want to graph them to consult the graph for plausibility. If it's a test question, maybe it'd be worth that much time. Here's one for you. Find the angle between these two vectors. To the nearest 10. What is the state? Without product, we won't need B dot W. If you did it like this, then that's not right. So the first thing you want to find is B dot W. B dot what? So if you look at your negative 3 and negative 5, you see how those are the two X values? Those are the two you want to find. B dot, I'm going to put you right in there. You can B dot W. But negative 3 times negative 5. Positive 8. And plus negative 1 times 2. Positive 8. That's your numerator. The magnitude of the yeah, that's what you were asking me about. So find the magnitude of well, in this case, negative 3, negative 1. So the magnitude of each is square root of 3 squared plus down to square root. So you're going to multiply, so you square each of those.
square root.
So right, magnitude v, in other words, the absolute value of v. Magnitude. And then a weird, and then
Each of those elements squared. What is three squared positive value?
and then one squared positive. So that's going to equal the square root.
So, split back into the calculator. We put it in the calculator.
So generally, that indicates some small number. The cosine inverse has such a tight range. Any error typically. So this should be 3 squared. So that you have I changed that Okay, so Maggie, tell me what this angle is. Very good. To the nearest 10th of a degree. Questions about that? So make sure you can reproduce that. You will have a quiz question, and then later on a test question based on this. Projection of U onto V. So here's our last formula for the day. If I want to project U onto V, remember I told you it's how far U travels along the path of V. Computer, enlarge. Thank you. I will use this formula. So U dot V over the magnitude of V squared multiplied by V vector. So the result will be a vector, not a scalar. So when I ask you for a projection, you're going to give me a vector as an answer. At minimum, hopefully a certain vector. But if you give me a scalar, rip, no partial credit. That's 100% wrong. Okay, so we're going to find the projection of U onto V. And remember that our numerator is U dot V. I'll just take that whole thing. Better sound. Too loud. Okay, so projection of U onto V. U dot V. We need to find that first. So that's -1 times 4 plus 5 times 6. -4 plus 30. 26. JT. Better late than never, brother. All right, so that's U dot V. That will be our numerator. Now we need to find the magnitude of V squared. And once again, remember that I taught you how to find the magnitude in that part 2. So that formula still works. But we're going to use the formula we learned in this section, which is the magnitude of V squared equals V dot V. So you see, all we need to do is find the vector dotted with itself. That will give us the denominator of our value we're going to scale the vector by. So V dot V is going to be 4 squared plus 6 squared, 16 plus 36, 52. So we've got a numerator, we've got a denominator. Now we're going to multiply those two in ratio form. So U dot V is 26 over 52, and that's going to be multiplied by vector V, which is, Isaac, what does 26 over 52 reduce to? Very good. So that's the answer to the first question they posited. He's a different highlighter. He's already used yellow version. The second thing they ask us here, write it as the sum of two orthogonal vectors, one of which is the projection of U onto V. Well, in order to do that second part, I want to write U, which is negative 1, 5, as the sum of two vectors, one of which is the projection of U onto V. So it's going to equal sum vector plus our projection. So this is the equation we're going to use to solve that second part. Okay, so how can we figure this out? Well, if we take these x components, I know negative 1 equals the x component of our vector in question plus 2. If I subtract 2 from each side, I see its x component is negative 3. And then for the y, I know that 5 equals y plus 3, and subtract 3 from each side, 2 equals y. So there's the answer. Those are the two vectors we would sum together to get that second part. Okay, questions about that? Projections. Projections. So far, you've learned how to take the dot product. You've learned how to find the angle between two vectors. And you've learned how to find the projection of one vector onto another. Those all will be represented on a quiz or a test. So we'll just work through this one together real quick. Luke, what should I find first here? Very good. So Mason, tell me what the values here would be for U dot B.
1 plus negative 3.
So that's 4 minus 3, which is 1. So there's U dot B. What should I find next? Randall? Magnitude of V squared. I did not, and that's a good answer for what comes next. So tell me what that would be equal to. Well, it's B dot B, which is indeed 1 plus 1. So it's 1 times 1 plus 1 times 1 if you're wondering where that came from. I did that mentally. As a teacher, it's important to be expository. In other words, to show your work every single step. So you find I do that by default at this point. Wasn't always true. Many years ago, I did not do that as well. If you think I go fast now, take me in 2008. So we now have everything we need to plug into this formula. So Anna, tell me what goes here. 1/2. And then tell me what goes here, Caleb.
One more.
Very good. Okay. So after I scale that vector, get this. I won't bother with the second half in this case because I'm not going to test for that anymore. Questions about anything? All right, cool. Projection with direction opposites. So we're going to use the same formula. I'll go a little faster this time because these can be a little tedious once you've seen a few of them. So U dot V, 4 times -3 plus 2 times 5, so that's -2. And then magnitude of V squared, that's going to be 9 plus 25, or 34. So what I've got here is -2 over 34 times -3 comma 5. So what is this one reduced to, JT? Good. Shame on you for using your calculator, but that is correct. I shouldn't say shame on you. It is my hope that you can do those calculations anyway. So negative times a negative is positive. Then negative times a positive is negative. So 3 over 17 comma -5 over 17. That is the projection of U onto V. We'll forego the second half of the problem again. Okay, so here's kind of an interesting problem. Now your book has a really convoluted way of doing this. They find a unit vector along a certain path. I do it with a little bit more geometry. You can choose to use the book's method if you like. So you got a 10,000-pound boulder sitting on top of a mountain that has an incline of 60 degrees. So, you guys in physics right now? It's going to look a lot like a physics problem. So I've got 10,000 pounds of rock sitting up here. What is the force required to keep the boulder from rolling down the mountain? We're ignoring the force of friction, which would be high in this case. Rocks are not spherical, and they certainly have a high friction coefficient, but we're pretending like it's perfectly spherical, and there's no friction coefficient. So you've got a vector on this boulder going straight downwards with this much force. So the vector is effectively this. And we want to know how much of that force is traveling along this pathway. Well, if we come down here to the horizontal, I can create a right triangle, and I see that this angle is 30 degrees. So the amount of force, if I have 10,000 pounds going straight downward, the amount of it that would be displaced along this path is the following. And if I punch that in the good old calculator, get negative 8660.25. It's also in pounds of force. So the additive inverse along this vector, to hold it still, would have to be have the magnitude of this. So the magnitude of the vector that's going to hold it back needs to be 8660.25. All right, so now for a brief homework assignment. Your task is page 506, numbers 2 through 20 even. Also, the quiz will be active starting here in just a few minutes. So make sure and think about how and when you should tackle that.